In this video, we introduce basic signals we used in the communication systems. The first signal is a sin0 signal, sin0 wave expressed by ex of t equals to a cosine 2 pi f naught t plus theta. So a is the amplitude, f naught, that's the frequency of the sin0 signal, and theta, that's the phase of the signal. In this course, we draw a lot of waveforms and we plot a lot. MATLAB is a helpful tool to help us in this perspective. So I'm going to use MATLAB to demonstrate the waveforms of this cosine signal, sin0 signal, in terms of the magnitude, frequency, in the phase. Now this is a MATLAB code to generate a cosine signal. So the magnitude is 5, frequency is 2, which means that this cosine signal should repeat itself 2 times in 1 second. So the phase, initial phase, first we can choose 0, and then I plot the waveform from 0 to 2 seconds. So therefore, theoretically, we should say 4 cycles because the frequency is 2. Let's run the program and see the figure. And you can see here the magnitude is 5, and this is a t in second. This is x-axis, time duration from 0 to 2 seconds. So this is a cosine signal. Cosine 0 at t equals 0 and phi equals 0, that's equals to 1. But a, this amplitude is 5. So we t as equals t at 0, this cosine signal at t equals 0, that's 5. So this is the magnitude is 5. And note that in the lab, we normally use the peak to peak value, so P to P value, which means that this signal P to P value will be 10 because the minimum peak, the minimum will be -5, the maximum will be 5. So peak to peak, that will be 10. That's the terminology we use actually frequently in the labs in this course. Okay, so let's see how many cycles from here to here. So the signal repeats itself, just 1 cycle. And then from here to here is another cycle. And from here, that's 3, that's 4. We can see we have 4 cycles in 2 seconds. Therefore, the frequency is 2. Okay. So now let's change the frequency a little bit. Let's change the frequency is 4. And we still want to plot the time duration from 0 to 2 seconds. Now we should say 8 cycles in total. So let's run the program. So you can see here we have 8 cycles total here. Here 1, 2, 3, 4, 5, 6, 7, 8. Okay. Next, let's look at the phase, the initial phase, phi here. Now phi, let's do phi equals to pi over 4. If phi equals to pi over 4, so convert it into degree, that will be 45 degree. Let's run the program. You can see here at t equals 0, cosine 45, that's 1 over square root 2, but multiplied by 5, that's about 3.5. Okay, so you can see here it starts here and finish here, 8 cycles, and the frequency is 4. So let's change back to frequency 2, and then we'll look at, you can see here, so that's total 4 cycles, a little more clearer. Now let's change to minus pi over 4. That's the phase will be minus 45 degree. Let's see what it look like here. So it look like when t equals 0, cosine minus 45 degree is also 1 over square root 2. So here is also 3.5 here. We can see it is 4 cycles as well. If start from here and finish here. So 4 cycles in 2 seconds. So the frequency is 2. The next signal we use a lot in communication systems is complex exponentials here. So ext equals to a e to power j 2 pi f naught t plus theta. A, f naught, and theta, that's the same definition of cosine signal here. Using Euler's formula here, e to power j phi or e to power I phi, they are the same. These two notations are the same because I and j notation complex number, I, j, all equals to square root minus 1 here. Then Euler's formula tells us that e to power j phi or e to power I phi equals cosine phi plus j sine phi. So Euler's formula we use a lot in this course, so we want to memorize that. So therefore, this complex exponential with function of time can be written as a real part function, real part waveform, and the complex imaginary part of the signal here. xr equals to a cosine, and xi, that's the imaginary part, that's a sine part, according to the Euler's formula here. This signal, complex exponentials, can be expressed into a polar form. So this is a magnitude of x of t and the angle of xt. So magnitude is a because the real part squared and plus the imaginary part squared, and then you take square root, you have cosine squared plus sine squared, that's y. Then that is 1. So therefore it is a here. And the angle is arctangent of the imaginary part divided by the real part. And this is equals to 2 pi f naught t plus theta. And this is a general formula. It depends on the signal in which quadrant. This is a video link that I made to review of complex numbers because it is very important to understand the complex number first, and then we can understand the complex signals, because complex signals is complex numbers changing with time. And in this video, I also demonstrate how to use MATLAB to help us to calculate the complex numbers. So MATLAB is a very useful tool.